In this chapter, we're going to start looking at the interaction between the electric field and different materials. Let's start out with conductors. Namely, we're going to begin by introducing the concept of the current density, and I want you to be able to relate that to a number of different quantities, such as the current, or the electric field, or the resistance. And as part of the process, also things like the charge. Let's start by talking about current density and current. Now, in many cases, because as you see with Gauss's law in integral form versus the differential form, a lot of the solutions that we're being able to solve mostly consist of the very small regions, because once you get to large regions and you want to use the integral form, you may not be able to have a nice solution. And so since we're mostly concerned about characteristics at a point or a very small region in many cases, the current density is a quantity that we use more in these analyses. So the current density, as you might imagine, it has the units of amperes per meter squared. It's the amount of current going through a surface area. So if we have, let's just say, a wire, and the wire has, in this case, a circular cross-section, and we have a certain amount of current flowing through it, so an amount of a bunch of charges moving at a velocity, so you have a current flow going through this surface area. In this case, our ds is going to be in this direction, and this is going to be our cross-sectional surface area, and we can describe the current that's going through the surface through the current density, J. And when we want to relate that to the current, we can see that the total amount of current flowing through this wire will be the surface integral of our current density with the dot product of this ds vector. So that's the relationship between current density and current. And when you integrate across the surface, that's the cross-sectional surface area that we're interested in. Another way to view the current density that I think is also important is to think of it more in terms of the mass flow rate. In other words, if we have a volume charge density rho v, and they're all moving at a speed of v, so rho v in this case is charge per meter cubed, and then if they're all moving at a particular velocity, so note this is a lowercase v referring to velocity, not uppercase with regards to potential. This will be in meters per second. In the end, if you do the unit analysis, you will get coulombs per second, which is amperes per meter squared. So this gives you amperes per meter squared. So that is also another definition of current density to keep in mind. So two ways to look at it in the case of, say, using traffic as an analogy. If you have a two-lane road, right, and each lane has X number of cars going through, you integrate that across two lanes. So you multiply that by 2. That gives you the flow rate, right? 2 x cars per second, right? If each lane has X cars per second flowing through it, and you have 2 lanes, then you have 2x cars per second flowing through. Another way to view this is if you have a total density of this number of cars, and they're moving at a particular velocity, if you multiply those together, you still get the same concept of the total amount of charge flow rate, so amperes per second, over the per unit area. One important thing to remember in this is that J is a vector, right? This is the amount of flow through this in a particular direction. And if you take the surface integral, you take the dot product with ds, and you get I is not a vector. So that's another concept that's really important to note. Note that there's no line on top of this I. It has some directionality to it in terms of its positive or negative sign, tells you whether the total amount of net current is flowing in the direction of this ds vector or in the opposite direction. But just remember, J is a vector and I is not. Let's continue our discussion between current density and charge by introducing the continuity equation. And if we think about the definition relating the current to charge, we can see that the current is the negative change in charge over time. The negative sign is referring to the fact that in our convention, we define outward flow to be a positive current flow. Or to put it another way, if I have a bunch of positive charges and I'm throwing them out, right? If I'm throwing them out, that's positive current going this way, and then so the amount of current that I have sitting here is going to be decreasing, right? So if I'm shooting out positive charges, that means that the total amount of positive charge I have is going down, and in this case we define that as positive current, so that's why we have a negative sign here. So if we plug that in, we're going to find that J dot ds is going to be equal to minus dq dt. Now let's do something similar to what we were doing with the electric field, and let's apply this to an infinitely small volume. So what we're going to do is we're going to look at a really, really small volume, and we're going to find all the net arrows. So we're going to add up, if there's 3 arrows going in, 2 arrows going out, then the net arrow for this small volume is going to be +1. Right? And remember what happened when we did this to the electric field. That gives us, in the electric field, that gives us the divergence of E, which is what? The charge density, right? So it's just something to remember. Now we're going to do that now these arrows are no longer electric fields, we're going to do that to the current density arrows. Now remember what we were doing when we were shrinking this to an infinite volume? What was that? That was where we started that was when we used the divergence theorem, right? So what we're going to do is we're going to take this J dot ds and we're going to apply the divergence theorem. So we're going to convert this to a volume integral of the divergence of J. Right, so remember, the divergence theorem is saying that if you do a surface integral, it's the same as if you did a volume integral over that region of the divergence. Let's equate that to the right-hand side. On the right-hand side here, we have the minus time derivative of Q. Now, another way that we can rewrite the total charge is the volume integral of the charge density. So now, if we equate these two quantities, this here and these two elements here, we arrive at the fact that the divergence of J is going to be equal to minus d rho v dt. Or the divergence of the current density is going to give you the change in the volume charge density over time. Let's take another look at this. One way that I like to think about this is, let's say this is a parking garage. Right? So the divergence of J is, again, as we talked about before, it's adding up all the arrows, right? All the arrows going in minus all the arrows going out. So in our parking garage analogy, that's like saying if I add up the total number of cars going in and subtract the total number of cars going out, that is going to give me the net change in the number of cars that's in the garage. So that's like, again, saying, if I had this person here counting the number of cars that's going into the garage, and then we plant another person here at the output, at the garage exit, and that person's counting the number of cars that are leaving the garage, and then these two people compare notes, add it all up. What's that going to be equal to? That is going to be equal to the net change in the cars in the garage. So that simple concept put in complicated scientific terms is called the continuity equation. And as you can see, this is a basic mathematical concept, right? So you can imagine, so there's actually this continuity equation also has a version that applies in hydrodynamics where you use that to describe water flow instead of current. So but when you convert it into physical analogy like this, you can see where it comes from. But bottom line is, tying it to a previous concept, the divergence of the electrical field tells you the charge density. The divergence of the current density gives you the change in the charge density. Let's wrap up our discussion by tying the current density to the voltage or the potential, as well as the resistance. So we'll also conclude with a formula that looks kind of Ohm's law-like. If we look at conductors, since we know that most of the movement is in the form of electrons, if we take a look at the electron charge density, so I'm going to call this rho sub E. Rho sub E is the same as rho sub V, except we're talking only about the electrons, so it's a negative charge density. And we'll also define the quantity, the mobility, mu E. We can define the overall drift velocity, I'll call that V sub D, is equal to minus mu E E. So this is I think this is probably the more straightforward way to relate mobility, is to see that it is the relationship between the electric field as well as the overall drift velocity that occurs, the movement that occurs on the part of the electrons as part of the electric field. Now let's use this concept to relate the current density to the electric field through the conductivity term. We can write that from our discussion earlier over here, we can write that the current density is going to be equal to the charge density of the electrons times the drift velocity, which once we plug in the formula for the drift velocity, we can write that the current density is going to equal to minus rho E mu E. So the electron charge density times the mobility, E, and we're going to call this overall thing sigma. So the conductivity, which is defined as minus rho E mu E, so the electron charge density times the mobility, with a negative sign because the electron moves in the opposite direction of current flow. If we define our conductivity this way, then we have the relationship that we can relate the current density to the electric field by saying that J equals sigma E. And now that we can relate the current density to the electric field, we can also say that the potential, we can also use our previously defined equation that the potential is the line integral of the electric field between 2 points, from the starting point to the final point. So we can then use that to relate the current density to the potential. Now let's apply this concept back to our initial cartoon of current flowing through a conductor, and we'll tie this to Ohm's law as we know it. I'm going to clear off this right-hand space here. All right, let's continue to stick to this situation where we have current flowing through a conductor. Let's say that this conductor has a length L, and our ds we're still going to keep in this direction. Our E field is going to be in the direction of the current flow. And let's also define the surface area of the conductor. We'll call this S. And as far as our potential is concerned, we'll take the potential from our initial position and then integrate upward to our final position. And if we define this as the positive direction, we can apply that formula we just wrote where the potential is the integral of E dot dl. In this case, if this direction is positive, right direction is positive, we're integrating the negative direction. If the field is constant throughout this entire length, then we can pull it out and we simply have that the potential is equal to E times L. We also have the relationship that the value of this constant electric field is going to be V over L. And that unit kind of makes sense, right? The electric field is in units of volts per meter. In this case, you can see that over the course of length L, the potential went across by V volts, and so you get volts per meter this way. Now let's plug this into the definition of the current density. So recall that the current density is equal to the current divided by the surface area, S, so I over S, and it's also going to be equal to sigma E. If we plug in our E equals V over L, then we'll get sigma V over L. And with that, we can then move some things around to solve and find that V is going to be equal to I L over sigma S. And if we call this whole thing to be equal to R, we're left with V equals IR. So this is kind of the one way that we can take a closer look at the definition of resistance in Ohm's law. You see that through our little cartoon derivation here, that the potential and the current can be related by the length divided by the surface area, and then with this extra factor divided by the conductivity. And that kind of ties into our intuition of resistance, right? If we have a fixed amount of resistance per unit length, the longer the resistor is, the more resistance we have. And if we take our water flow analogy, the larger the surface area, then the lower the resistance, right? Or the more car lanes there are, then the less resistance there is, the more current flow there can be. And so through this, I'm hoping that you can use our basic equations of relating the current density to the electric field and the electric field to potential with this cartoon conductor picture to derive some kind of a Ohm's law-like expression, which kind of tells you how to relate conductivity to the familiar quantities of current and voltage. So in summary, we went over a lot of material here, but we start out by defining the current density, which is quite often more frequently used than current because we use the differential forms of Maxwell's equations a lot, and the differential form, in this case, the equivalent of current would actually be current density. We defined it as the current over the cross-sectional area of the conductor in question. We also defined the continuity equation, which in differential form tells us that the divergence of the current density is going to be equal to negative the change of the charge density over time. And then we also saw that the current density can be related to the electric field through this term, this conductor term here, which is related to the mobility of the carriers and the charge density. And with that, we plug that into our general concept of a conductor to create an expression that's Ohm's law-like, where we can see how the conductor relates the basic geometries of the conductor to the relationship between the voltage and the current.